Hello, so we come to the last and concluding lecture in this series on differential equations. So today's lecture will be looking at some odds and ends, or maybe is ahead if you like. So the issues that we discuss today will be as follows: some uses of differential inequalities, but this will be very similar to the way we worked with linear differential equations, and then we'll converge towards a uniqueness theorem, but we shall not exactly reach there. We shall not state the uniqueness theorem. The pendulum equation again. We started this lecture series by deriving the pendulum equation. That was the first differential equation that we derived, and we shall also end by looking at the pendulum equation a little more closely, and then a few concluding remarks. And so let's begin. How to use differential inequalities. Now let us look at this differential equation 4.1. dy by dx equals y into x plus y, with the initial conditions y of 0 equal to 0. You see, this differential equation 4.1 is a Bernoulli equation. It's a Bernoulli equation, and so you want to divide by y squared, but unfortunately you cannot. Why? Because y of 0 is 0 and division by 0 is not allowed. So how would you solve 4.1? Well, you see that the 0 solution is already a solution. Take the constant solution 0, it satisfies the differential equation. The derivative of 0 is 0, and the right hand side is also 0. So plug in the constant solution y equal to 0 in 4.1, and you see at once that it's a solution of the differential equation. It also satisfies the initial condition y of 0 equal to 0. But have we completely solved 4.1? How do we know that there are no other solutions of 4.1 satisfying y of 0 equal to 0? Maybe there are others besides the 0 solution which will satisfy 4.1. How do we rule out that possibility? We need a general theorem, a general uniqueness theorem that guarantees that the 0 solution is the only solution of 4.1 and that there are no other solutions. So you see the need for a general uniqueness theorem already in this very simple situation. So let us go back to the very first lecture where we discussed differential inequalities, where we knocked off some terms in the differential equation and got a differential inequality when we were discussing escape to infinity in finite time. Well, so let's look at the differential equation 4.1. dy by dx equal to xy plus y squared. The y squared term is always positive. So let us look at the differential equation. Dy by dx equal to xy plus y squared. The y squared term is always positive. So let's see. So we can write dy by dx minus xy greater than or equal to 0. I had knocked off the y squared term from the differential equation 4.1. For the 4.1, I have knocked off the y squared term. So from the differential equation, I got the differential inequality 4.2 dy by dx minus xy greater than or equal to 0. Now, how do we proceed? Now, suppose if in 4.2 you had an equality instead of an inequality, then 4.2 would be a linear differential equation, right? So how would you proceed in that case? You would multiply the 4.2 by e to the power minus x squared by 2, right? But do the same thing here. Never mind, it's an inequality, but e to the power minus x squared by 2 is always positive. So I can jolly well multiply 4.2 by e to the power minus x squared by 2, and the left hand side of 4.2 becomes an exact derivative, namely ddx of y of x into e to the power minus x squared by 2 greater than or equal to 0, which is 4.3 in the displayed slide. Well, what do we do now? We have to integrate 4.3. We have to integrate 4.3. So let's proceed. You got the following situation. Let's see. You got a function phi of x which is always non-negative. on an interval AB. Then we can say integral phi of x dx from A to B is surely non-negative. You will agree with me on that. Why? Because what is the integral? The integral is the area under the graph, the area under the graph y equal to phi of x between x equal to A, x equal to B and y equal to 0. But what does this inequality tell you? The inequality tells you that the phi of x, the graph of phi of x lies above the x-axis. If the graph lies above the x-axis, then the area under the graph is going to be always positive. And that's all that you need to say to prove this. So in particular, if you have two functions fx and gx, and if fx is greater than or equal to gx on the interval AB, then integral a to b fx dx will be greater than or equal to integral a to b gx dx. How do you get this? You get this from the previous one. Simply take phi equal to f minus g. Simply take phi equal to f minus g in the previous one and you get this one. Okay, so let's apply this. So let's go back to the slides. You see, you got 4.3. So I say that integral on the left hand side will be greater than or equal to integral on the right hand side. In other words, the integral of the derivative from 0 to x. I am going to integrate both sides of 4.3 from 0 to x. Okay. So I am going to integrate both sides from 0 to x. When you integrate a derivative, you use the fundamental theorem of calculus. So you got d dx of y of x e to the power minus x squared by 2 greater than or equal to 0. So integral 0 to x d dt of y of t e to the power minus t squared by 2 dt greater than or equal to 0. Of course, in the definite integral, the variable is a dummy variable. So let's use the fundamental theorem of calculus. Y of x e to the power minus x squared by 2 minus y of 0 e to the power minus 0 squared by 2 greater than or equal to 0. This is 1 and y of 0, remember, was 0. Therefore, we get y of x is greater than or equal to e to the power x squared by 2 into 0, which is 0. So we have concluded that the solution is non-negative. We have concluded that y of x is non-negative if x is greater than or equal to 0. Now we shall show that y of x is actually equal to 0. Let's proceed. Now we know that y of 0 is 0 and y is continuous, and therefore if the value of the function at the origin is 0, then the value of the function must be less than 1 in a certain piece around 0, namely 0 to c. So on the interval 0 to c, we know that y of x must be less than 1. If y of x is less than 1 and y of x is already non-negative, y of x squared must be less than or equal to y of x. So let us go back to the differential equation. What does the differential equation say? It says dy by dx equals xy plus y squared, but now we have seen that y squared is going to be less than y. So let's use this inequality now. So since y squared is less than y, from 4.1 we get the differential inequality dy by dx is less than or equal to x plus 1y on the piece 0 to c. So again do the same thing, again imitate as if you are solving a differential equation. Proceed as though you are going to solve a linear differential equation, namely you multiply the differential equation by e to the power integral px dx. What is px in this case? Minus x plus 1. And then you will conclude exactly as we proceeded just now, y of x is less than or equal to 0. And so combining the two, we see that y of x must be identically 0 on this piece 0 to c. But now we want to show that not only is y of x identically 0 on the piece 0 to c, it must be 0 everywhere. You can actually show that it is going to be 0 everywhere. Proceed by contradiction. Suppose it is 0 up to a certain interval, after which it becomes positive, then try to arrive at a contradiction. Be slightly careful if you are working this proof out. Okay. So now let me give you a couple of exercises. Try the same idea on these two differential equations that you see in the slide. The same idea of knocking out some terms, getting an inequality and proceeding. So I worked out one example in detail and I am asking you to try out two others. So the two differential equations are dy by dx equal to y into y plus square root of 1 plus x cube. The other one is dy by dx equals y into y to the power 3 plus sine squared x. For both these differential equations, y of 0 is 0. And so by inspection, you see that 0 is a solution. What you need to establish is that it is the only solution. So proceed as I have indicated in the last exercise. So what's the point of this exercise? Isn't there a simpler and more direct approach to arrive at this conclusion? Each time you encounter a situation where you have to divide by y or y squared, as it happened in the Bernoulli equation, and the initial condition says y of 0 equal to 0, are we going through this rigmarole each and every time? What you need really is a general uniqueness theorem. General uniqueness theorem that can be directly employed off the shelf. You pick up a uniqueness theorem. Importance of proving such uniqueness theorem is now slowly dawning upon us. And how do we prove such uniqueness theorems? The point that I want to make is that these examples that we have just worked out are rather typical models of reasoning which will give you a proof of the uniqueness theorem. Idea is to obtain a differential inequality and then proceed exactly as we solve a linear differential equation. And we shall not prove the general existence theorem, but the key ingredient is the idea in the following slide. So suppose f of t is a non-negative function on an interval ab such that f of t is less than or equal to a plus b integral a to t fs ds. Inequality 4.4. That's a hypothesis. A and b are constants and f is non-negative. Then the conclusion is inequality 4.5, namely f of t less than or equal to a exponential of b times t minus a. Idea of this proof is exactly similar. Call the right hand side of 4.4 as capital F of t. Capital F of t is a plus b integral a to t fs ds. Then notice that little f is less than or equal to capital F. Little f is less than or equal to capital F, and capital F evaluated at little a is capital A. 4.7. What do you do next? Differentiate 4.6. Differentiate 4.6, what do you get? df by dt equal to bf, right? You use a fundamental theorem of calculus to differentiate 4.6. df by dt equal to b times little f. But b times little f is less than or equal to b times capital F. You got a differential inequality. You will proceed exactly as you do with a linear equation. Multiply the differential equation by e to the power minus b into t. A is capital A, f of little a equals capital A, and then incorporate that into your integral. You get f of t into exponential of minus b into t minus little a less than or equal to a, which is what we wanted to prove. So the proof of this exercise is the proof of this little result exactly follows the same pattern, and this is a key ingredient in the proof of the uniqueness theorem. So now we shall move on to the next part of this lecture series and the last part of this lecture series. The pendulum restlessly continues to swing, punctuating the inexorable march of time. So the pendulum keeps swinging and it calibrates the interval of time for you. So let's go back and recall what the pendulum equation was. d2y by dt squared plus g over L sine y equal to 0. That is equation 4.9. Now what we do is that let us multiply this equation 4.9 by a factor of dy by dt. What happens? You get dy by dt into d2y by dt squared. Okay. So throw in a factor of 2. You get 2y dash y double dash. What is 2y dash y double dash? What are you going to get if you differentiate y dash squared? If you differentiate y dash squared, you are going to get 2y dash y double dash. Look at the next term, sine y into y dash. How do you get sine y into y dash? You differentiate minus cos y. If you differentiate minus cos y, you will get exactly sine y into y dash. So what happens when you multiply the differential equation 4.9 by y prime? When you multiply the equation 4.9 by y prime, the left hand side of the equation becomes an exact derivative. That's exactly what you see in the next display in the slide. d dt of dy by dt the whole squared minus 2g by L cosine y is 0. So integrate this and you get dy by dt the whole squared minus 2g by L cosine y equals e. Again I use the letter e for the constant of integration. There is an obvious reason for it. Identify the terms in 4.10 that represent the kinetic energy and the potential energy. The first term dy by dt squared is somehow related to the kinetic energy and the second term is somehow related to potential energy. You might have to multiply it by some constant. You might have to add a certain constant, the reference potential, but essentially equation 4.10 spells out the law of conservation of energy and we are going to refer to equation 4.10 as the energy equation. We are going to call it the energy equation. Okay. Now let us prescribe initial conditions. Y of 0 equal to 0 and y prime of 0 equals c, where c is a positive constant. What does this mean? It means the pendulum starts from the mean position with an angular velocity c, with an initial angular velocity c. You give a slight push to the pendulum from the mean position and the pendulum starts oscillating. Incorporate these initial conditions in the energy equation, right? You have got the energy equation 4.10. Put t equal to 0. Put t equal to 0. dy by dt at t equal to 0 is c. And cos y when time t equal to 0 is cos 0, which is 1. So equation 4.10 simply reads c squared minus 2g by L equals e. So e is c squared minus 2g by L. That's what I'm saying. So the right hand side of 4.10 energy equation has been replaced by c squared minus 2g by L. So the next thing to do would be to take the cosine term on the right hand side. If you take the cosine term on the right hand side in equation 4.12, you will get dy by dt the whole squared equals c squared minus 2g by L into 1 minus cos y. Now recall the trigonometric identity. 1 minus cos y is 2 sine squared y by 2. So you get dy by dt the whole squared equals c squared minus 4g upon L sine squared y by 2, equation 4.13. Now, you might look at equation 4.13 and you will be happy because you got a first order differential equation. Equation 4.13 is a first order differential equation. Our immediate impulse will be to take the square root and say dy by dt equals square root of c squared minus 4g by L sine squared y by 2. And that's a variable separable equation. We are very happy. We can separate the variables and we are going to integrate. Okay, you do that. You are going to run into an integral that you cannot compute. And that integral is the elliptic integral. So, the elliptic integral that I mentioned a few lectures ago appears here in connection with the pendulum equation. So, we have dy by dt the whole squared equals c squared minus 4g by L sine squared y by 2. So, since y dot of 0 is c, which is positive, the derivative at time t equal to 0 is positive, let us take the positive square root of 4.13 on both sides and we get dy by dt equals square root of c squared minus 4g by L sine squared y by 2, which has been called 4.13 prime. 4.13 prime is a variable separable equation and we proceed in the usual way. We divide 4.13 prime by square root of c squared minus 4g by L sine squared y by 2 and then integrate both sides with respect to t over the interval 0 to t, noting that y of 0 equal to 0. So, what do we get? We would get 0 to y dy by square root of c squared minus 4g by L sine squared y by 2 equals t. Now, we put sine y by 2 equals u. We get 1/2 of cos y by 2 dy equals du or dy equals 2 du by square root of 1 minus u squared, and the integral in the last slide transforms to t equal to 2 upon c integral 0 to sine y by 2 du divided by 1 minus k squared u squared into 1 minus u squared. This last displayed integral is an elliptic integral. So, we are naturally led to elliptic integral in the study of the pendulum equation. Since we cannot undertake a study of elliptic integrals, we must abandon this line of investigation and we must take a completely different route. Any attempt at trying to solve this 4.13 by the method of separation of variables is going to lead you into trouble. Now, we shall leave this elliptic integrals and try to understand the qualitative behavior of the solution without solving the differential equation. Remember, we have seen this in the past. The idea of differential equations is that we must try to get information about the solutions without explicitly solving the differential equation. So, we shall assume that c squared is bigger than 4g by L. Let us assume that c squared is bigger than 4g by L and look at the right hand side of 4.13. The right hand side of 4.13 can never become 0 because if c squared is bigger than 4g by L, since sine is between -1 and 1, the right hand side of 4.13 is obviously never 0. And so, the derivative dy by dt must always keep the same sign. It must always be positive or it must always be negative. And initially, look at 4.11, the derivative was initially positive, so it must be positive forever. So, the derivative is positive always That means that y of t must be a monotone increasing function of time. The function yt is monotone increasing with respect to t. Also, since the right hand side of 4.13, let us go back to 4.13. What is the lowest that 4.13 can become? The lowest the right hand side of 4.13 gets to is c squared minus 4g by L. 4.13, the right hand side of 4.13 is least when the sign factor is 1, and c squared minus 4g by L is positive, say call it a squared. So what do we see? So if you put c squared minus 4g by L as a squared, then we see that dy by dt must always be bigger than or equal to a. So y of t must be bigger than or equal to at. So y of t is not only monotone increasing with time, it is increasing at least as fast as at. It is greater than or equal to at, and so as time progresses, the angle is going to keep on increasing and it go to infinity. But it's an angle, remember, the pendulum is swinging, and so first the angle will go from 0 up to 2 pi, and then from 2 pi it will go to 4 pi, 6 pi, 8 pi. So that what it's saying is that the pendulum is performing circular motions. So the pendulum, the C is so large that the pendulum goes over the top, completes the circle, and it keeps performing circular motions. So after one circuit, the angle goes into the interval 2 pi to 4 pi. After the second circuit, it goes into the interval 4 pi to 6 pi, and so on. So if c squared is bigger than 4g by L, the pendulum has too much energy, it starts performing circular motions. Next, let us look at what happens if c squared is less than 4g by L. And here I am going to give you some very simple calculus exercises. Show that the angular velocity dy by dt must become 0 at some point of time, and yt must attain a maximum in some point of time. That particular maximum value will be the amplitude of the pendulum, and the time at which that happens will be a quarter period, and so the period of the pendulum will be 4 times t naught. Now, suppose not. Suppose it doesn't happen. That means that the derivative is never 0. Then what happens if the derivative is never 0? Then again y of t must be monotone increasing as before. But this time y of t cannot reach pi, because if y of t reaches pi, then sine squared y by 2 will become 1 at that particular point, because y by 2 will be pi by 2 and sine pi by 2 is 1. And then right hand side of 4.13 will become c squared minus 4g by L, but c squared is less than 4g by L, remember? So the right hand side of 4.13 has become negative, but the left hand side is a square, and that's a contradiction. So that cannot happen. So the angle of the pendulum, the y of t, can never reach pi. So we see that y of t is monotone increasing and it doesn't come anywhere close to pi. So it must have some limit as t goes to infinity. Y of t must have a limit alpha as t tends to infinity. Remember, a monotone increasing function must either go to infinity or it must have a finite limit. This finite limit cannot be pi, and so it has to be less than pi. That's what we have seen. But now the differential equation itself says that the derivative must then have a limit, because what is the derivative? Dy by dt squared is c squared minus 4g by L sine squared y by 2. Y has a limit, so sine squared y by 2 has a limit. So the right hand side of 4.13 has a limit. In other words, the derivative square has a limit. Dy by dt square has a limit. So dy by dt has a limit because it's always positive. So you've got a situation where you've got a function which goes to a limit, and the derivative also has a limit. But think geometrically. Think of a function which settles down to a limit as t goes to infinity. That means that the graph is becoming flatter and flatter. So you expect that the derivative, if it has a limit, it must be 0. That's exactly the case. If f of t is a differentiable function such that f of t and f prime t have finite limits as t goes to infinity, then the derivative must compulsorily go to 0. I just explained this to you geometrically, because f of t has a limit basically means that the graph is becoming horizontal. It is becoming flatter and flatter. And so the derivative, if it has a limit, it must actually be 0. But can you prove it rigorously using calculus? I recommend you do it using the mean value theorem. Let's apply the mean. Instead of relying on the geometrical intuition, let us back it up with rigorous reasoning. Let us apply the Lagrange's mean value theorem on the interval t comma t plus 1. F of t plus 1 minus f of t is going to be for some c between t and t plus 1. But let t go to infinity. The c in the mean value theorem is between t and t plus 1. So as capital T goes to infinity, the c also goes to infinity. And so we have the equation f of t plus 1 minus f of t equals f prime c. The left hand side goes to 0, we know, because f has a limit, say L. So f of t plus 1 goes to L, f of t goes to L. So f of t plus 1 minus f of t goes to 0. Therefore, the right hand side f prime c must go to 0. So the derivative compulsorily must go to 0. So we are given two different ways of understanding this. So now let's get back to the pendulum. We know that y of t, the amplitude, is monotone increasing. It can't come anywhere close to pi. It must have a finite limit. In that case, the derivative y prime t must go to 0 as t goes to infinity. So what do we have? We have that as t tends to infinity, y of t has a finite limit alpha, which is less than pi, and y prime of t has a limit, and this limit, as we have seen, is 0. Now where do we go from here? Observe that y double prime plus g upon L sin y is 0. Now y has a limit, y prime has a limit, and so this equation y double prime plus g upon L sin y equal to 0 tells us that y double prime has a limit as t tends to infinity. But the calculus lemma now must tell us that y double prime must necessarily go to 0, and therefore the pendulum equation will again give us that limit of y of t must be 0, which means that alpha must be 0. But then that means the pendulum is stationary, it is not swinging at all, and that's a contradiction. So now explain why the point t0 in the last exercise must be a local maximum. It's easy, the first derivative is 0. But what is the second derivative? Go back to the original equation of the pendulum. Y double prime plus g over L sin y is 0. So y double prime is minus g over L sin y, that will be negative. So second derivative is negative, so the point is a local maximum. So the pendulum starts swinging, it reaches a maximum, and then it has to swing back because it can't go beyond that. And then one can again argue that it must have a minimum value. But what prevents the maximum value being something and the minimum value being something else? So the maximum value could be, say, 60 degrees. Maybe the minimum value is minus. How do I know that? How do I know that it swings to the same amount to the right as it does on the left? Look at problem number 5. Problem number 5 tells you that the extent to which it goes to the right is the same as the extent to which it goes to the left. That's because we have said that y of 0 is 0, and so the solution must be an odd function. Here we appeal to a uniqueness theorem, which we have not proved, the evasive uniqueness theorem. We can also solve exercise 6 without using the uniqueness theorem in a slightly different way. Let us see. We use the energy equation. Okay. So, assume that the maximum amplitude is alpha and the minimum amplitude is minus beta. So, look at the energy equation. Dy by dt the whole squared equals c squared minus 4g upon L sine squared y by 2. But the left hand side is 0 when y takes the values alpha or minus beta, because alpha is a maximum and minus beta is a minimum. And therefore, we get c squared equals 4g upon L sine squared alpha by 2 and c squared equals 4g upon L sine squared beta by 2. So, equating the two things, we will get sine squared alpha by 2 equals sine squared beta by 2, from which we deduce alpha equal to minus beta, which completes the discussion of problem number 6. Alright. So, that tells you that if c squared is less than 4g by L, the pendulum exhibits oscillatory motion. It goes to the right and then it comes back and it has a minimum, and then again it starts moving forward and it executes oscillatory motion. Whereas if c squared is bigger than 4g by L, it executes circular motions. So, what happens at the critical value c squared equals 4g by L? What happens if c squared equals 4g by L? Is it that the pendulum takes forever to reach the topmost point, the angle pi? We must investigate that and see whether that happens. It turns out that in this critical case, when c squared equals 4g by L, we are singularly lucky. We can actually complete the integration of the differential equation. So, let us see how to do that. So, remember c squared equals 4g by L. So, go back to equation 4.13. C squared equal to 4g by L. So, the 4g by L can be taken common, and we get 1 minus sine squared y by 2, that is cosine squared y by 2. So, equation 4.13 greatly simplifies in the critical case. So, we got equation 4.14, dy by dt the whole squared equals 4g by L cos squared y by 2. Now, observe that if y prime of t naught equal to 0 at some finite time t naught, the right hand side of the last equation will give you that y of t naught must be pi and y prime of t naught must be 0. But notice that the constant function y of t identically pi also satisfies the pendulum equation, and it also satisfies the initial conditions 4.15. And so, once again the evasive uniqueness theorem that we have not even stated can be appealed to, and we see that our solution was constant solution. But that is not the case, because if it is a constant solution, the derivative must be 0. We are assuming that the C is 4g by L. So, we conclude that y prime t never vanishes, and we may take the positive square root of both sides of 4.14. So, we have the following variable separable equation for the critical case: dy by dt equals twice root g by L cos y by 2 and y of 0 equal to 0. So, let us try to solve equation 4.16 by separating the variables. So, bring the cos y by 2 on the left hand side and integrate. You get log secant plus tan. You get log secant y by 2 plus tan y by 2 equals root g by Lt. Denote the right hand side by s. That root g by Lt you simply denote it by s, and just for simplicity you put y by 2 equal to theta. Then the last equation can be written as log secant theta plus tan theta equal to s, or secant theta plus tan theta equals e to the power s. So secant theta plus tan theta equal to e to the power s, equation 4.17. Take the reciprocal. Take the reciprocal, we get secant theta minus tan theta equals e to the power minus s. Adding and subtracting, we get secant theta equal to 1/2 of e to the power s plus e to the power minus s. 1/2 of e to the power s plus e to the power minus s will be denoted by cosh x. Cosh is the hyperbolic cosine of s. And then what is the tan theta? Tan theta is 1/2 of e to the power s minus e to the power minus s. That is hyperbolic sine. So we got this equation 4.19. Secant theta is hyperbolic cosine and tan theta is hyperbolic sine. So now we see a relationship between hyperbolic functions and trigonometric functions without having to go into the complex domain. By staying in the real domain, we pass from the trigonometric functions to hyperbolic functions via real change of variables. This function theta of s given by 4.19 has a name. It is called the Gudermanian in honor of Christopher Guderman. This name was given by Arthur Cayley in 1862. A very interesting history of this Gudermanian can be found in page 312 of Krystal's Algebra, volume 2, which was published in 1900s. In fact, it's published before 1900s. This is a later edition. The inverse of the Gudermanian appears in cartography and navigation. Remember that we already encountered cartography when we discussed orthogonal trajectories. And again cartography comes in. And it comes in cartography and navigation in connection with the Mercator's projection. So what Mercator was trying to construct, he was trying to construct a map. He was trying to construct a map in which the loxodromes on the sphere are getting mapped as straight lines on the map, on your plane map. Well, you'll ask me, what are loxodromes? Let me explain it to you. Now, loxodromes are curves on the globe with the property that they cut the longitudes at the same angle. The curve cuts all the longitudes at the same angle, at a constant angle. Why are such curves important? They are important because remember that in navigation concerns ships. Ships are huge, mighty objects. When you want to go across the ocean from one point to another point, you might think that the best option is to take the shortest path. The shortest path is a great circle joining the 2 points on the surface of the earth. But the problem is that when you travel along the great circle does not intersect the longitudes at the same angle. The angle of intersection keeps changing. So the ship will have to be steered continuously. The direction of the ship has to be continuously changed. And doing it with a mighty object like a ship is going to be very difficult and very expensive. So the ships do not travel along great circles, rather they travel along loxodromes, curves which cut the longitudes at the same angle. So now if you take a loxodrome on the surface of the earth, what will it correspond on your plane map? The map is a planar object. It's printed on a sheet of paper. And Mercator was trying to devise a map in such a way that these loxodromes on the globe correspond to straight lines on the map. In an attempt to do that, he encountered this inverse of the Gudermanian function. So I'll give you two references for this. One of them is already cited before, chapter 8 of John McCleary's book, Geometry from a Differential Viewpoint. I mentioned this book earlier. And the second book I'll mention is H.L. Resnikoff and R.O. Wells, Mathematics and Civilization. Very interesting book. The second one is a very interesting book. He also talks about navigation, mathematics and navigation, how calculus comes into navigational problems. So here are some exercises in the good Riemannian. Show that theta of s is 2 tan inverse of e to the power s minus pi by 2. And show that the good Riemannian is an odd function and is an increasing function. Well, as far as this problem is concerned, there is very little for you to do. Differentiate this equation, theta of s. You straight away differentiate the 2 tan inverse term, that is 2 upon 1 plus e to the power 2s into e to the power s. That's evidently positive, and so it's an increasing function. How do you check that it is an odd function? Replace s by minus s. Replace s by minus s. You get 2 tan inverse of e to the power minus s. But what is tan inverse of e to the power minus s? It is tan inverse of 1 upon e to the cot inverse of e to the power s. But what is cot inverse of e to the power s? Pi by 2 minus tan inverse of e to the power s. And the 2 times pi by 2 will become pi, and the pi minus pi by 2 becomes pi by 2. So theta of minus s is pi by 2 minus 2 tan inverse of e to the power s, which is minus of theta of s. So theta is an odd function. The next problem is very interesting because a similar one appeared in JEE 2014. The problem that appeared in JEE 2014 is to integrate a cosecant theta to the power 17. Now, when you take an odd power of a secant and an odd power of a cosecant, you know that if you start integrating by parts, you will have to do it over and over again many times, and it's not going to be fun. So you want a way to avoid integration by parts over and over again. So how to integrate an odd power of a cosecant or an odd power of a secant? The good Riemannian will help you to do it. So secant theta to the power 17 d theta. So how do you do this? Put secant theta plus tan theta equal to e to the power s. So what do you get? You get, put secant theta plus tan theta equal to e to the power s. So you get secant theta equal to hyperbolic cosine. So differentiate. So secant theta tan theta d theta will be equal to hyperbolic sine times ds. So secant theta d theta will be hyperbolic sine s ds divided by tan theta. But tan theta equal to hyperbolic sine s ds. Therefore, secant theta d theta equal to ds. So, your integral secant to the power 17 theta d theta will become integral secant to the power 16, which is hyperbolic cos s to the power 16 times ds. Let us now incorporate the limits of integration. Remember the equation? Secant theta equals cos s. So when theta equal to 0, s would be 0, and theta equal to pi by 3 would correspond to s equal to log 2 plus root 3. That's easy for you to check. So what do we get? The integral would transform to 1 upon 2 to the power 16, 0 to log 2 plus root 3 e to the power s plus e to the power minus s raised to the power 16 ds. And the hyperbolic cos is simply e to the power s plus e to the power minus s by 2. And so you can expand it by the binomial theorem. It's much easier, particularly when you see definite integrals present. You don't have to integrate by parts repeatedly. And similarly, you can try the cosecant theta to the power 17. Here you put cosecant theta minus cot theta equal to e to the power u. Okay, so I hope you enjoyed this short trip into the world of differential equations, and I'd like to only say a few words to conclude. I've taken you through many interesting parts of differential equations. We saw a lot of geometrical examples, we saw examples from physics, we saw examples from biology, we looked at the orthogonal trajectories, we looked at lots of applications, we looked at astronomy and stuff like that. And I've given you many references, and I'll give you two more references. And the first reference is a very beautiful book by G.F. Simmons, Differential Equations with Applications and Historical Notes. The second edition is what I'm referring to. It's published by Tata McGraw-Hill. Third edition has also come out, but the second edition will suffice for our purposes. This is a very good book. It is a delightful reading. The historical essays on eminent mathematicians make delightful reading. The first 80 pages are accessible to students, that they are accessible to you. Numerous applications with geometry, curves of pursuit, the Brachester-Krohn problem, and orthogonal trajectories are available. So the book is available in Indian edition. And the second book that I'd like to mention is Spivak's Calculus. Spivak's Calculus is a very beautifully written book. It's a carefully written book on calculus. And on chapter 17, you will see a derivation of Kepler's laws from Newton's laws of motion. And that was published in 1994. So now our journey has come to an end, and I hope you enjoyed this journey into the world of differential equations. I'd like to say goodbye, but before doing so, it's my pleasure to thank a number of people, which I shall do so now. I shall begin by thanking Professor Neela Nataraj, the head of the Department of Mathematics, my colleague, and the IITB coordinator of this program. And I especially thank her for giving me an opportunity for delivering these lectures, and more importantly, for her constant encouragement and support, particularly at times when my enthusiasm was going low. She gave me the much needed impetus for going on. And then I'd like to thank my colleague, Professor Shantanu Dey, who has listened to these videos, who have worked through the exercises, and for his assiduous task of proofreading, and for giving me a very big list of corrections which I have incorporated. Then I'd like to thank Professor Vikram Gadre, the head of CDEEP, for offering us this beautiful CDEEP studio with its state-of-the-art facilities, and Professor Niladri Chatterjee from IIT Delhi, who is a coordinator of this program. I'd like to thank Aditya Maheshwari, the PhD student of my department, who helped me with those figures. And last and most importantly, I'd like to express my heartfelt thanks to the technical staff who have been constantly working and who have put up with my pestilence all the time. And to them I owe a lot, and they are Mr. Tarun Negi, Mr. Sandeep Jadhav, Mr. Sugandh Sawant, and Mahesh Ghadi. To all of them I express my thanks, and I thank you all my students. You goodbye. Thank you very much.